Okay, so you see we have discussed about the pulse mode in quite details. Now it's time to look more into the details of the spectrum, which are the basically outputs of the detector. So we have talked about the detector mode, right, current and pulse modes, right. Now let us talk about the detector output, which is basically spectrum. Okay, now in this regard, a very important concept is pulse height spectra or spectrum, right. So this is what we are going to talk about next. Okay, now so our topic is pulse height spectra. Well, you see, when we operate a radiation detector in pulse mode, each individual pulse amplitude carries important information regarding the charge generated by that particular radiation interaction. This we have discussed, okay, in the detector. Now, if we examine a large number of pulses, then what we will first thing we will observe is that the amplitudes are not all same. They are different. Okay. Now what can be the reason for variations? Well,
sir, আপনি কি স্ক্রিন শেয়ার করছেন?
So these variations, as I was telling you, it might be due to differences in radiation energy, right, deposited, or incoming radiation as well, right. Another fluctuation reason is that inherent response of detector to monoenergetic radiation. What does this mean? এর মানে হচ্ছে যদি আমার charge Q is deposited, right, suppose a gamma ray deposits some charge but at different energies, although it is not possible, but suppose it happens, then what will happen if the inherent response of the detector is the same for both of them? Then we will get an amplitude corresponding to the charge which is deposited. However, if the response of the detector to a single gamma energy is different for different gamma energy, then the amplitudes, they will not be in a linear proportion to just the charge being deposited, because the important information of the detector response will also be there. I will talk more about it in details later today. Okay, now the pulse amplitude distribution is a fundamental property, pulse amplitude distribution of the detector output, which is important because it gives us information about the detector incident radiation, and also using the amplitude we can get information about the detector itself, whether the detector is working properly or not. Okay, now you see the most common way of displaying pulse amplitude information is through the differential pulse height distribution. This is a very important concept. Now let me show you an example of this distribution. তোমরা এই নামটা কি আগে শুনেছো, this pulse height distribution? here on your screen you can see the pulse height distribution, differential pulse height distribution that I was talking about. Okay, now it basically what you are seeing is a hypothetical distribution. Okay, now you see the abscissa is a basically linear pulse amplitude scale here that runs from 0 to larger values than the amplitude of any pulse observed from the source. Now you have already encountered such cases in your experimental lab, whether in graduation or master's degree, first, second semesters. Third semester practically is yet about to start. Okay, so I am just talking about what you have already seen, but probably you don't know the very exact details of what is happening, or maybe some of you already know that. Now, as I was saying, you see, we have the abscissa, we have a quite linear pulse amplitude scale, right? Going from higher values, 0 to higher values. What about ordinate? It is basically the differential number of pulses observed with an amplitude within the differential amplitude increment dH here divided. So basically what we are doing is differential number of pulses dn divided by the differential pulse increment dH. So this is dn by dH here. This is dn by dH, and this is just the pulse height h. Okay, now what do we get from this? You see, so the horizontal axis has the units of volts. What about the vertical axis? This will have the units of volts inverse, number divided by amplitude, right? Now you see the number of pulses. Let me write down the number of pulses whose amplitude lies between two specific values, say h1 and h2. They can be obtained. It can be obtained by integrating the area under the distribution between h1 and h2, right, as I am showing here in this figure. Okay, h1 and h2. So this is basically the number of pulses having amplitudes lying between h and h2. So let us write it down. So what is it? So we can write it as h1 to h2 dn dh dh. Let this be equation 1. Now the total number of pulses represented by the distribution. So total number of pulses, basically n0, this is just we can obtain by integrating the area under the entire spectrum. It means here this is just the differential part, and what about the integral part? So integral part is basically, you see here the spectrum. So integral part is basically the entire area. So this is dn by dh. This is what I mean when I am doing this. So 0 to infinity dh. Okay. Now it is important to note that most of the time we are accustomed to look at the shape of the differential pulse height distribution to display important features about the source of pulses. Okay, so most of the time we are talking about the shape of the pulse. So, shape of pulse height distribution is important, right? Why? Because it tells us about several features of source of pulses. Now, the maximum pulse height here, you see, so the maximum pulse height observed, what is this? H5 is simply the point above the apsica at which the distribution goes to 0. Here the distribution goes to 0. Now peaks in the distribution such as H4, how many peaks are there? Here only one, H4. So this is the peak. Okay. They indicate pulse amplitudes about which a large number of pulses may be found. So this is basically our pulse amplitude, right? On the other hand, valleys or low points like this, say for example H3, this is a valley. So this is a peak, this is a valley, right? They indicate values of the pulse amplitude around which relatively few pulses occur. So this means pulse amplitude, again this one, for large number of pulses, and here same pulse amplitude, but for small number of pulses which could be found, right? Now the physical interpretation of this differential pulse height spectrum basically involves area under the spectrum between two given limits of a pulse height. Remember that the value of the ordinate itself, that means dn by dh, has no physical significance until it is multiplied by an increment of the apsica. Now let me, after discussing this, let me talk about another way of displaying information about the pulse distribution of pulses amplitude, and that is the integral pulse height distribution. Okay, so basically we are talking about pulse height distribution, and there also we have two types. One is differential pulse height distribution and another is integral pulse height distribution. Okay. Now this is what we are going to talk about now. So yes, here you can now see this. So this was the differential pulse height spectrum, and correspondingly we have the integral pulse height spectrum over here, this one. Now this basically shows the integral distribution for the same pulse sources for which the differential spectrum is shown above here. Now the apsica in the integral case is the same pulse height scale shown previously, but the ordinate now represent the number of pulses whose amplitude exceed that of a given value of apsica h. So the ordinate n must always be a monotonically decreasing function of h. Because why? Because you see, fewer and fewer pulses lie above an amplitude h. that is allowed to increase from 0. Now because all the pulses have some fixed amplitude, the value of the integral spectrum at h is equal to 0 over here must be the total number of pulses observed, n0, right? So previously what was n0? N0 was differential spectrum, we have to do this. But in the integral case, we can easily find n0. So this one is the n0 over here, right? Again, what about the value of h5? You see, the value of the integral distribution must decrease to 0 at the maximum observed pulse height, h5, because after that there is nothing. Had there been something, it would not be 0 over here. It can be 0 over here, but not over here. Okay. What if it was 0 over here? What would have happened? You see, if it was 0 over here, let me show you. Suppose the spectrum was something like this, dip. Then as a result, you will also observe some dip over here, but not 0. This 0 means that there is nothing beyond, no counts. Okay, and that's why it is 0 in this range. Fine. Now the differential, it is important to remember that both of them, this differential and integral curves, they actually convey the same information, and in fact they can be derived from one another. So if I give you a differential spectrum of a source, okay, if I give you this, then you should be able to derive the integral spectrum, and vice versa. The amplitude of the differential distribution at any pulse height is given by the absolute value of the slope of the integral distribution at the same height. Okay. Where peaks happen in the differential distribution, say for H4, local maxima will occur in the magnitude of the slope here in the integral distribution. On the other hand, wherever there is a minima in the differential spectrum, corresponding regions of minimum magnitude of the slope here, minimum magnitude, are observed in the integral distribution. Now because it is easier to display subtle differences by using the differential distribution, this is most of the time used. And even in your experiments, we also use this in the lab. We also use this differential spectrum. Okay. So we have talked about basically the output, spectrum, features, pulse height spectrum, differential pulse height spectrum, integral pulse height spectrum. Right. Now let me give you some examples of this spectrum experimentally. So let me give you some examples of counting curves. So examples of counting curves. So as I was mentioning before, you see, when radiation detectors are operated in pulse counting mode, a common situation often arises in which the pulses from the detector are fed to a counting device with a fixed discrimination level. So, what does this mean? You see, when radiation detectors are operated in pulse counting mode, sometimes it can happen that the pulses from the detector are fed to a counting device with fixed discrimination. So, pulses fed to device with fixed discriminator. This means that anything below this discriminator we will not count, we will not record. Why it is there? Sometimes this is important for getting rid of noise, electronic noise, right? Which is always there in detector in one form or the another form. Okay. Achha. Now let me show you here some examples. Now signal pulses in this case, they must exceed the discrimination level. Say discrimination level টাকে আমরা নাম দিচ্ছি HD, discrimination level. So it must exceed, otherwise we will not record. So pulses must exceed HD in order to be registered by the counting circuit. Now এর মানে তাহলে তোমরা জিজ্ঞেস করবে HD কি fixed? No, it is possible to vary it as well in the course of measurement. কখনো আমার নয়েজ বেশি, কখনো আমার নয়েজ কম, তার জন্য আমি এই ডিসক্রিমিনেটর লেভেলটাকে আমি পাল্টাতেও পারি। Now let us assume that HD can be varied between 0 and H5. H5 means this one, this spectrum. আমি যদি HD টাকে vary করতে পারি, so if HD can be varied between 0 and H5, তাহলে কি হয়? Let us see. এর জন্যে কিরকম পালস আসে। Now তাহলে যেটা করব আমরা, we do a series of measurements which I have shown you here, right? Discriminator level, এই যে দেখো এইখানে fixed discriminator level. So আমি লিখছি, দাঁড়াও। So HD is basically, it means that signal pulses must exceed HD to be registered by the counting circuit, and এটাকে বলা হয় discriminator level. Okay, and I can also vary the HD পুরো সার্কিটে। একটা কথার কথা বলছি, যদি আমার এই রকম স্পেকট্রাম হয় আর আমি সাপোজ HD এইখানে করে দিলাম, what will I observe? I will only observe this part of the spectrum from here onwards, right? This part. I will not observe this part of the spectrum. বোঝা গেল? So again আমি বলছি, দেখো যদি এই রকম হয় HD এইখানে আমি সেট করি, so only I will be observing this part, and this part of the spectrum it will not be there. But again I can change the HD value as I want. তাহলে যেটা হবে, যদি আমি এইদিকে নিয়ে যাই, I will be observing this part only, and this will I'll be getting rid of. Okay, now again the same thing I am showing over here. You see, I have done a series of measurements, say, where the number of pulses per unit time is measured as HD is changed through a sequence of values between 0 and H5, which I was mentioning before. যদি ওই রকম হয় তাহলে কি হবে দেখো এইখানে। Now see, এই যে এর জন্য যেটা হবে যে আমরা এখানে এই রকম স্পেকট্রাম দেখতে পারবো। Okay, so let me show you some more examples. Suppose this is a spectrum. Okay, the same spectrum, and again yet another spectrum. Okay, suppose here is HD. Next time I have changed the HD over here, and this time I have changed the HD over here. So what will I observe is that I will be observing, in this case, only this part. This part will not be there. In this case, I will be observing only the part which is shaded. So only shaded part registered in counter or detector. However, in this part only here. Now, as I was telling you, so this is the effect of changing the discriminator level. Right, this is what we have done. Now, sometimes for a particular radiation detector, it is possible to vary the gain. Or what is gain? Basically, it is an amplification provided for charge produced in radiation interaction. So, what is gain? Gain is basically amplification provided for the charge produced in radiation interactions. Now, this variation could be accomplished by varying the amplification factor of the linear amplifier circuit that I will talk about later on, which is present between detector and counting circuit. So we have detector and many other circuits, and then we have the counting circuit. And this part, amplification, is done in the linear amplifier part over here. I will talk about these various sections of the electronics in my next lecture. Now, as I was saying, this variation you could be seen by, we can vary the amplification factor between in the linear amplifier, right? Now, the figure that I showed you previously, this figure here, basically it shows you the differential pulse height distribution corresponding to, you see, how many measurements? 3 different measurements, where we have 3 different values of voltage gain or amplifications. So HD is same in each time. Unlike this figure over here, where I am changing the HD, in this plot you see I have fixed the HD, but so here HD fixed, gain changes, right? So this is this plot, whereas in this plot over here we have HD changes but gain fixed. বোঝা যাচ্ছে? আসিফ, হ্যাঁ বলো।
স্যার 8 নম্বর পেজে যে ফিগারটা, ওটাতে ওয়াই অ্যাক্সিসটাতে কি প্লট করা আছে? এনটা
না, ডিএনডিএইচ, এটা তো ডিফারেনশিয়াল পালস হাইট স্পেকট্রাম না, সো অলওয়েজ ডিএনডিএইচ থাকবে।
8 নম্বর পেজে,
8 নম্বর হিয়ার ডিএনডিএইচ, দিস ইজ জাস্ট ডিফারেনশিয়াল পালস হাইট স্পেকট্রাম।
আচ্ছা, নিচের ফিগারটা,
নিচেরটা আমি আসছি, আমি বলছি, নিচেরটা বলছি, নিচেরটা
আর
বলছি।
স্যার আরেকটা কোশ্চেন ছিল যে এইচডিটা স্যার চেঞ্জ করছি কিভাবে আমরা?
এইচডিটা ওইখানে তোমার একটা ভোল্টেজ নব থাকে, যেটাতে দিয়ে তুমি ডিসক্রিমিনেটর লেভেল চেঞ্জ করতে পারো। জাস্ট যেরকম আমরা মানে এটা ইলেকট্রনিক্স মডিউলে থাকে। ইফ ইউ কাম ইন দ্য ল্যাব, আই উইল শো অল অফ ইউ হাউ ইট ইজ অ্যাকচুয়ালি ডান ইন এক্সপেরিমেন্টস। ওকে,
আচ্ছা, মানে এইচডিটা ইন ভোল্টস?
Yes, of course. দেখো, this is axis, pulse height axis. So this means a unit কি থাকবে? Volts. So HD is also in volts, and this is DNDH. So unit is volts inverse. Right?
হ্যাঁ স্যার।
Okay. Now, so where was I? Yeah, so here you can see the differential pulse height distribution corresponding to 3 different values of voltage gain applied to the same source of pulses. They are not different, but same source of pulses. Now, we can define the value of gain as the ratio of voltage amplitude for a given event in the detector to the same amplitude before some parameter was changed. Now actually how it is done I will show you in the lab, but this is a definition of that. Now you see the highest voltage gain will result in the largest maximum pulse height. You see why? As you increase the gain, you are basically stretching the spectrum, okay, and as a result of which more and more part of the spectrum goes above your discriminator level, and so you will be able to register more and more part, and you will be able to see more and more part, okay. But note that the area under the differential curve distribution will be constant. You see, area is always this constant. So even though we can stretch, so basically changing gain stretches the spectrum, but area remains same. Of course, this should be true. Okay. Now you see, let us discuss this part, this figure. When the gain is 1, we will not observe any counts, because all the pulses will have values smaller than HD. So no counts. Right. What about this here? We will observe some counts which are so little bit greater than HD over here, and here we will observe the majority of the counts. Now you see an experiment we can carry out in which the number of pulses recorded is measured as a function of the gain applied, and this is sometimes called the counting curve. You can see over here, this is the counting curve. Such a plot I have shown, and in many ways it resembles basically the integral pulse height distribution. Okay. Any questions? So basically we have a mirror image of the integral distribution. However, because small values of the gain will record no pulses, whereas large values, you see, will result in counting nearly all of the pulses. Right. So this is counting curve, and what we saw before, this is basically counting plateau. Now it is important to note that sometimes in certain detectors like GM counter or scintillation counters, the gain can be varied by changing the applied voltage to the detector. Although the gain may not change linearly with voltage, the qualitative features of the counting curve can be traced by a simple measurement of the detector counting rate as a function of voltage. And most of the time during an experiment, the first thing we have to do is to select an operating point which has maximum stability. And at that point, the plateaus, we always try to find it. And so as a result, we have a counting curve. And from there, like this, from this counting curve, the voltage, operating voltage is selected to lie at the point of minimum slope on the counting curve. I think you must remember that we did the same thing with the GM counter. But remember, that time instead of gain, you just use the detector bias voltage. Right. So as I was saying, why? Because the gain in GM counter can be varied by changing the detector bias voltage or applied voltage. Okay. let me discuss a little bit more about the pulse height distribution and also energy spectrum. So, you see, basically to determine the energy spectrum of particles emitted by a source, what we do is we measure with the help of detector and appropriate electronics the pulse height distribution. So it is other way around. So to measure the energy spectrum, we measure the pulse height distribution using detector plus electronics. Right. Now, for doing that, we require certain fundamental requirements for both the detector and electronic systems. So, there must be certain requirements. And what are they? The first requirement is that the particles should deposit. So, the particle should deposit all of its energy. Okay, or a known amount or known fraction, known constant fraction of it in detector. This is important. It should not be that it will deposit an unknown amount. So it will be a known constant fraction of it, or best all of it. What is the next requirement? The next requirement is that the voltage pulse produced by the detector, so voltage pulse produced by detector should be proportional. It must be proportional to energy of particle dissipated in it, or at least again a known relationship should exist between energy dissipated and pulse height, or known relationship should exist between energy dissipated and pulse height. Okay, the third important requirement is that electronic amplification should be the same for all pulses. Okay, let me give you an example of this last part. Suppose I have got a pulse, and as a result of, say, changing the gain, I have got two pulses of different energies. Now, if I change the gain, as a result of which both pulses are multiplied by different factor, then it is not required, then it is not correct. We do not want that. What we want is that we want the amplification to be same for all pulses. Linearity in response will be there. Okay. So you see, since the relationship between the pulse height distribution and energy spectrum depends on these requirements, it is very important to remember them. Okay. Now, what about charged particles? Well, you see, charged particles deposit all of their energy in the detector as long as their range is shorter than the size of the detector. Whereas gamma, they do not necessarily deposit all of their energy in the detector regardless of the detector size. This is why you know this. Exponential and Lambert, right? I is equal to I0 e to the power minus mu x. This gamma attenuation relation, you know. What does this mean? This means that there will always be a probability for gamma ray escaping because of its exponential attenuation nature. What about neutrons? Well, you see, neutrons are detected indirectly through other particles produced by nuclear reactions. Now, I already talked about these things during my first lecture. I'm just revising. So, the energy deposited in the detector depends not only on the energy of the neutron for neutron detection, but also on the energy and type of the reaction products. Okay. Now, you see, the events that transform the particle energy into a voltage pulse are statistical in nature. That also we know. Random behavior. As a result, even if particles deposit the exact same energy in the detector and the amplification is the same for all pulses, the output pulses will not be the same. This is very important, but also a sad thing. Right, but this is reality, nature. So let me again write it down. You see, the events that transform the particle energy into a voltage pulse are statistical in nature. Right. And as a result, what happens is that even if all particles deposit exactly the same energy in the detector, and the amplification is the same for all of them, right? For all the pulses, for all pulses. But as a result of this, what will happen is that the output pulse will not be same, but have a constant distribution. Okay. Okay. Any questions? As I was telling you, if there is some radiation incident on a detector, then not all energy, charged particle, neutron, depending on what type of radiation it is, charged particle, neutron and gamma ray, you see, so depending on that, we can have incomplete energy deposition, complete as well as incomplete energy deposition in detector, right? So what will happen is that because of this effect, incomplete energy deposition, the shape of pulse height distribution will be different from the source. So as a result of this, the shape of pulse height distribution will be different from source energy spectrum. এর মানেটা কি হলো দেখাচ্ছি, দেখো এর মানেটাই হচ্ছে, সাপোজ আমার কোনো সোর্স আছে, ঠিক আছে, there is a source, আমি আবার যদি ডিএনডিএইচ দেখি, সোর্স থেকে কোনো একটা মোনো এনার্জেটিক এনার্জি নিয়ে কোনো একটা গামারে বেরোচ্ছে, কতগুলো গামারে বেরোচ্ছে দেখো, এখান থেকে আমি এই জিনিসটা পাচ্ছি, জাস্ট দিস থিং, দিস ইজ হোয়াট এমিটেড বাই দ্য সোর্স, আই নো. So this is basically source spectrum. So what is this? Basically energy spectrum of particles emitted by source, right? Correspondingly, আমি ডিটেক্টরে কি পাবো? What will I observe in the detector? In the detector, I will see measured spectrum. measured spectrum. And what will be the measured spectrum? You see, the measured spectrum will be something like this. Dekho, this is again E0. So এইটা হচ্ছে এর আগে আমি যেটা বলছিলাম, there will be a distribution of energy, not a single energy. This is distribution of energy. So just a second. So basically we have, as I was saying you, there are two features. One is distribution of energy deposited. এটা আগে আমি তোমাদের বলছিলাম. Another thing is that, but this distribution of energy deposited, this corresponds to full energy deposition. আর এই রকম নেচার কেন হচ্ছে, এই রকম ভোতকা নেচার মার্কা কেন হচ্ছে, এই নেচারটা এই রকম ফ্ল্যাটও হতে পারতো. দিস ডিপেন্ডস অন দ্য রেসপন্স অফ দ্য ডিটেক্টর বেসিক্যালি. অ্যানাদার থিং দেখো এইখানে এই পার্ট, অ্যান্ড হোয়াট ইজ দ্যাট? দিস পার্ট ইজ ডিউ টু incomplete energy deposition. Okay, so you see the source spectrum and the detector spectrum, they are entirely different in nature. Okay, any questions? Yes, so we have talked about the pulse height distribution, energy spectrum, source spectrum. Now it is again very important to recapitulate and also talk about the energy resolution of a detection system. Right, now you see the quality of the performance of a detector system used for energy measurements is characterized by the width of the pulse height distribution. So this is characterized by width of pulse height distribution, and this is obtained with particles of the same energy. With particles of same energy or monoenergetic source basically. Right, so even in the case where each particle deposits exactly the same energy in the detector, the pulse height distribution will not be a single line. যেটা আগে আমি দেখালাম তোমাদেরকে previously, I just showed it to you. Remember the pulse height, this was the source distribution and this was the experimental distribution. So it is never this is the detector spectrum and this is the source spectrum. Now you see it is never a line, but there is a finite width. So basically we have a finite width. Now as I was telling you, what are the various reasons of this finite width? There are in fact three very important reasons for the finite width. Number one, statistical fluctuation. Statistical fluctuation in the number of charge carriers produced in detector. Number two, electronic noise in the detector or in the electronic system, say amplifier, preamplifier. Number three is incomplete collection of charge in detector. Right, so we have a finite width. Okay, now you see what we will do is we will characterize this. So this is how we do that. As you can see in the spectrum, the width of this distribution basically is measured at the half of the maximum of this bell-shaped curve, and this width is denoted by this capital lambda, or this is known as FWHM. HM, full width at half maximum. Now, the ability of the detector to identify particles of different energies is called the energy resolution. So, ability of detector to identify particles of different energies is energy resolution. Okay. Now it is either given in terms of this delta, or sometimes it is given as the ratio. So either delta or the ratio, and this ratio is written like this: R as a function of E0 is equal to gamma by E0. So this energy is E0, and corresponding the width, the full width at half maxima is gamma. So this energy resolution is sometimes given either as gamma or as the ratio. So this has units of volt or keV if energy, and this has no units since this is a ratio. Okay, basically this is a percentage. Okay, now the most important elements affecting the energy resolution of a detector are the three statistical factors. Basically the three factors, right, which I mentioned in this picture over here. Now let me discuss the first effect, or the effect of statistical fluctuations on energy resolution. So let us consider first a monoenergetic source of charged particles which is being detected by a, say, silicon semiconductor detector. Okay, we can also use a gas field detector as well. Now since we are talking about a silicon semiconductor detector, right, so some energy, monoenergetic, it is falling over here. Now the average energy W needed to produce one electron hole pair, EH pair, in silicon, how much is it? It is basically 3.66 eV. Okay, although the energy gap, remember, the energy gap is 1.1 eV. Now this difference between this W and EG shows that part of the energy of the incident particles is dissipated into processes that do not generate charge carriers, right? Now any process that consumes energy without producing electron hole pairs is of course useless to the generation of the detector signal. So if the energy deposited in the detector is E, suppose energy deposited in detector is E, then the average number of charge carriers is how much? E by W, right? Just a second, তোমরা 2 minute দাঁড়াও একটু. Now, if the processes of the electron hole generation are purely statistical, if processes of electron hole generation are statistical, then Poisson statistics will apply. And the standard deviation of the number of pairs will be just E by W. Okay, now it is observed that fluctuations are smaller than what this equation, say equation number 2, gives us. So what is the observed? So you see, the observed statistical fluctuations, they are expressed in terms of Fano factor. You can check Leo or Knoll's book and you will find the details of this Fano factor. This is what I am also talking right now. So what is Fano factor? This is basically actual standard deviation of number of pairs produced, electron hole pairs produced, divided by number of pairs produced. Or this is actual standard deviation, right, of number of pairs produced divided by number of pairs produced. So if we use equation number 2, we will have sigma is equal to F into E divided by W. This is equation number 3. Now the values of F, they lie between 0 and 1. These are the two extremes. Okay. Now what is the meaning of F is equal to 0? 0 means that there are no statistical fluctuation in the number of pairs produced. And that would be the case if all energy was used for the production of charge carriers. Okay. What about F is equal to 1? F is equal to means that the number of pairs produced is governed by Poisson statistics. Okay. Now it is important to remember that for semiconductor detectors, the values of F lies between 0.2 to 0.5, whereas for gas filled detectors, same F values, this is for not, just a second, I did a mismatch. So basically for gas filled detectors it is this value 0.2 to 0.5, and for semiconductor it is not this one, but it is very small. Okay, it is 0.06. This is important. Okay, now value of F less than 1, as I was saying, this means that the generation of the charge carriers does not exactly follow Poisson statistics. Right. Since Poisson statistics, close the door. Since Poisson statistics, you see, applies to outcomes that are independent, so it seems that the ionization events in the counter are not independent but interdependent. Okay. Now the width of the Gaussian distribution is related to the standard deviation sigma by this relation, you see. And this is 2.355 W into sigma. This is an important result. Now if we combine the previous two results, then we will have this relationship, which is okay. So this equation basically shows that the width gamma, which is due to the statistical fluctuation, is roughly proportional to the square root of the energy, the Fano factor being a weak function of energy. Right. Now let us compare the contribution of statistical fluctuations to the resolution of different type of detectors. So different detector comparison. So for a certain energy, say same energy, we will do the comparison. So for the two detectors, let us write down R1 by R2 is equal to gamma 1 by E, same energy as I am talking about, gamma 2 by E, and this is basically gives me W1 F1 divided by W2 F2. So what does this tell us? So one thing that we can obtain, very important piece of information, is that the resolution is better for the detector with smaller average energy needed for the creation of charge carrier pairs and also smaller Fano factor. So this is the reason for better energy resolution of a semiconductor detector, because semiconductor detector, it has W of the order of 3 eV and F is much less than 0.1. Whereas for gas field detector, we have W is of the order of 30 eV and F is of the order of 0.2. Okay. Hello.
বন্ধ হয়ে গেছিল মানে।
আচ্ছা ঠিক আছে। So as I was saying, this is the reason why the energy resolution of semiconductor detector having the smaller values has better energy resolution than a gas field detector. Now let me talk about the next topic, which is the effect of electronic noise.
স্ক্রিনটা দেখা যাচ্ছে না।
আচ্ছা দেখছি আমি। Effect of electronic noise on again energy resolution, right? Now what is electronic noise? Basically electronic noise, this thing, if this is voltage and this is time, then we have this is electronic noise. What is this? So basically electronic noise consists of a small voltage variation around the zero line with average value Vn not equal to 0. Okay, average is not equal to 0. Now to see the effect of the noise on the energy resolution, let us consider pulses of constant height V. Okay, now in the absence of the noise, the full width at half maxima of the distribution of these pulses is 0. However, if the noise is present, then what happens is that the full width at half maxima of the distribution of, if the noise is present, then what happens is that the noise variation, noise voltage variation, or you can say noise pulse, they will be superimposed on the pulse produced by the particles. Let me show you the graph. Yes, so as I was saying, in the absence of the noise, you see, because of the noise, what is happening? Yeah, here you see. So what is happening is that the noise voltage variation or noise pulse is superimposed on the pulse produced by the particle, and this results in the recording of the pulse sites that are not of equal height alone. So initially this is because of, now this is due to noise pulse, right? However, actually previously it was like this. So without noise pulse, You see the difference? So what has noise pulse? It has sort of modulated, right? And this is the effect. And the pulses, this is what I have shown you. So I have shown you here the pulses which are superimposed on the noise, as a result of which they show a distribution with a width. Dekho? They show a distribution of the width that depends on the standard deviation of the noise. Okay. So here we have a Gaussian distribution centered at voltage V, which has a width equal to this value. Now remember that this width gamma n is due to the noise only, and it has got nothing to do with the statistical effects on the detector. So this is width due to noise only. Okay. Now sometimes we use the concept of signal to noise ratio. You must have heard this. So sometimes we use the SNR, signal to noise ratio, and that is basically the mean pulse height divided by the noise standard deviation, just by V by sigma n. Or we can write, you see, like V by sigma n is equal to 2 ln2 V by this gamma due to noise, or we have 2 ln2 divided by R, whereas R is given by the previous expression we talked about before. So as a result, let me write down finally R. We can write 2 ln2, there will be 2 here as well, and here as well, I missed out, divided by V by sigma n. And this shows that higher the signal to noise ratio is, the better the energy resolution becomes. You see, other things being equal, of course. Okay, now let me talk about the last two parts very briefly. Let me talk about them. So it is the effect of incomplete charge collection. Now basically the effect of the incomplete charge collection in gas field detectors is small compared to the effect of the statistical fluctuations. However, in semiconductor detectors, the incomplete charge collection is due to trapping of charge carriers, that we know. The amount of charge trapped is approximately proportional to the energy deposited in the detector, and that is again proportional to the energy of the incident particles. Because of this reason, you see, the resolution is affected by the trapping effects more at higher energy than at lower energy. Now, so trapping effects depend on the material of which the detector is made, of course, and on the radiation damage which is sometimes suffered by the semiconductor. Sometimes we incorporate the effect of the incomplete charge fluctuations in the statistical fluctuations itself. So with all these three effects, we are now ready to write down the total width. So we have discussed. So now we can write down the total width due to, or the total energy resolution. Total E resolution. And this we can do by adding in quadrature the contributions from statistical effect, from the noise, and from incomplete charge collection. Thus, we can write this as D, so plus N. So here we have included statistical as well as incomplete charge collection part, and here we have included the noise part. Okay, any questions? বোঝা গেছে?